Okay, so today we're gonna talk about congruency and similarity. That means congruent and similar figures. This is a pretty easy lesson actually. I'm not gonna take that long to explain it to you. Just keep in mind, congruency, you gotta think about same size, same shape, same side length, same angle measures, right? On the other side, similarity will keep always the same shape and the same angle measures, but you're not gonna be able to get the same size, neither the same side length. So every single time I think about, or I need to figure out whether two figures are congruent or similar, I gotta think about their shape, their size, the measure of their angles, and the measure of their sides, okay? Now, if you think about that, we can come back. Remember when we were talking about rectangles and squares and how every single square can be a rectangle, but not every rectangle can be a square? Well, it's the same thing. Think about how all congruent figures would actually be similar because the shape and the angle measure part actually agrees with similarity, right? So all congruent figures are going to be similar, right? But if we go the opposite way, so that means if we want to go from similar figures to congruent figures, not all similar figures are going to be congruent figures. So maybe that's something we need to keep in mind. And that is all congruent figures are similar, but not all similar figures can be congruent, right? Just keep that in mind. Now let's think about these two figures I have over here. As you can tell, the length of this little rectangle is 2 units, right? But then the length of this rectangle is 4 units. And then the width here is 1 unit, and the width here is actually 2 units. Would they be congruent? Can they be congruent? Well, they can't, right? Because of course we are not using the same size. That's probably the first criterion I want to use. Not the same size, right? They do have the same shape though, but all these characteristics here gotta be acquired at the same time. That means I gotta keep all of them working at the same time. So even though they have the same shape, they don't have the same size. So they're not gonna be congruent, all right? So if they're not congruent, then we need to understand that we just need to go to similarity, right? And just think about how similarity would work and see if this is gonna work for it. So the thing about these two is I need to think about how the similarity is working. In this case, I have the same shape, right? I do not have the same size. I do have the same angle measures because we know we have right angles in all figures, right? And the lengths of the sides gotta be actually committed to the exercise. So if you think about 2 units here, the length of the side is actually 4 units, so it's double, right? It is double. And if we think about the width, here's 1 unit, but here we have 2 units. So it is also double. So we can actually conclude here that because of the sides are now doubled, then we can see how the shape number 2, which is a bigger rectangle, can be similar to the shape number 1, which is a smaller rectangle, right? So in this case, we know they're similar figures. But how about we have, can you tell me what would happen if we would have a figure like this that is not going to have 3 units, but 4 units, but now it's going to have 3 units of length and 2 units of height? Well, yes, we know it's not they're not going to be congruent, but if we look at the similarity between them, it's not going to happen either. Why? Because of the length here. Here, the width, it is doubling, so we know we have double measures over here, but in the length, the double measure is not working because we have 3 units here. So if one side is increasing at some ratio or at some rate, then all sides gotta increase at the same rate. If one side is increasing double, but the other side is not, then we cannot say they are going to be similar figures, all right? We need to keep the same rate of increasing lengths for all sides, okay? So in this case, just keep in mind that part. This new example now is not similar. The example before with the 4 units over here, it was similar, okay? That's one thing we need to keep in mind. The other thing we need to keep in mind is that if I want to compare corresponding sides, then I need to know what corresponding sides are, right? Or corresponding parts, actually, because we can have sides and angles too. So if I give this shapes names as A, B, C, D, E, F, G, and H, right? Now we know we have rectangle ABCD and rectangle EFGH. And then we will know that corresponding parts gotta be in terms of the shape of the figure, okay? So corresponding parts over here, we know AC, the side AC is gonna be corresponding to what? Corresponding to what? To AG, right? And we know BD is gonna be corresponding to FH, and AB is gonna be corresponding to EF, or CD is gonna be corresponding to GH. Again, corresponding parts is, you had it on your book, corresponding parts are always gonna be in terms of the very same place where the side or the angle is at. Okay? Just talking about different figures, but I'm looking for the same location. In the case of the angles, angle AC, D, gotta be corresponding to what? To angle EGH, right? That makes sense. That's actually true. So just keep that in mind for corresponding parts. Now, if we come back to comparing those, how do I compare those? How do I compare corresponding parts? Especially, how do I compare corresponding sides? Because there is actually a very specific way to compare corresponding sides. Well, we can actually use fractions. We can use fractions to compare corresponding sides. How does that work? Well, here in the case of the width, we can talk about the width, right? There's a relation between the width in the smaller rectangle and the length of the width. Well, that sounds kind of redundant, right? The width here in the smaller rectangle and the width here in the greater rectangle. So I can compare them, so I can actually get a relation between those. So the width relationship, it's going to be what? we can actually work it out as a fraction. So we are going to use a ratio word. Remember the ratio word we talked about a few weeks ago? And ratio doesn't mean anything different than just comparison. We're going to compare, and we're going to use a fraction to do so. So here, I know I'm going to take the 1 unit I have in the width for the rectangle. I'm going to compare it to the 2 units I have in the greater rectangle. Now, if we want to get rid of units, because centimeters, kilometers, yards, or inches, whatever you want to use, when you want to talk about number relationships, you can just get rid of the units for a minute and write down just the numbers. So I can actually say the relationship in the width is 1/2, okay? Or 1 to 2, which are the measures we already have. Now, if I want to think about the length relationship, the length relationship here is going to be what? 2 units. 2, in this case, 3 units. So that is 2/3. Okay? Now, be careful that I am not going to get confused. I need to specifically know what are the corresponding sides so I'm able to build a fraction.